Maybe it's on the more button.
There we go.
Oh, there you go. Now you do.
No, I'm ready. Yeah, good. All right. So let me go back to sharing and. Okay, hopefully you all can see the slides I'm sharing there. And good morning. Anyway, welcome everybody to this year's ROCKE-3D tutorial. We skipped last year. We did it once during the pandemic, and now we're in the post-pandemic stage. So we're all sitting here together in this cozy room without masks. Who thought that would be possible 2 or 3 years ago? We would be considered heretics. Today we have myself, Michael Way. Kostas Sigouridis is here. You can see him in the owl camera. He's waving his hand. Chris Kalos is here. He's going to chat about some of the model, and Igor Alienov. Igor, maybe you can say hi. Maybe the camera will. The camera's over here.
Okay.
Perfect. Okay. So you see your instructors, or instructors is a strong word for what we are. But anyway,
Yeah.
we'll see how it goes. So to begin with, we have, as you can see, the email addresses for everybody sitting up there. And these slides I will share with you all after today, or maybe in the break. I meant to send it before, so I apologize about that. So let's just dig in. We have a lot of breaks planned, as you can see in the lunch break for those of us here to sustain energy. And then we have a long Q&A at the end as needed. You don't have to stay here for an hour. Typically, we don't, but we're very happy to chat with you all further about things you might be curious about. I have noticed that some of the students have attended the tutorial before or have already been using the model, and they might have some of the more interesting questions. So this is the one time per year when you get all of us together in one room, and this is the time to ask questions. So we encourage that very strongly. Okay, so that's day number 2. And for some reason I have my screen in a funny way, so I'll have to look at the display over here. Anyway, so I thought the first thing we should do is just mention a little bit about, what a general circulation model is. I think you all know, so we're not going to go into the details here. But you can see, at least for the model that we're using here, ROCKE-3D, we're on a latitude, longitude grid, as you see in the upper left there. With, in our case, generally use the Socrates radiative transfer scheme with 40 layers. If you use the native GIST scheme, which is much more restrictive, and we'll get into details about what we mean by that, that's 20 layers. And the ocean we typically use is a 13-layer ocean. And then we have 6 layers in the land surface part of the model, which is quite complex. And you can see some of the ocean and land surface and atmospheric processes there down in the lower left. One thing that people should always remember is that the timescales that you simulate with these GCMs are quite short, at least if you're a geologist. We're talking about maximum 10 to the 4th year type things. I think the longest simulations we've done is about 10,000 Earth years, I would say. And you can see the vertical range, at least if you run an Earth type model, is about 65 kilometers. We can't simulate atmospheric escape in this model. We cannot simulate thermospheric or exospheric processes in this model. This is a lower atmosphere model. As I say here, it's limited to shallow atmospheres. We cannot do mini Neptunes or these kinds of extended envelope type worlds. So if you wanted to use ROCKE-3D for that, you're in the wrong place. You have to use somebody else's model. Right. And this is kind of an abstract representation of the model where you can see there are, the ocean model, the land, and vegetation parts of the model. The vegetation is really from modern Earth, just so you know. There's a sea ice component of the model, land ice component of the model. There's chemistry and atmosphere, and there's some shared utilities. And there's a coupler, of course, that brings all that together, which makes the model a whole. And I'm going to go through a few things of, what the model is good for to re-emphasize these kinds of things. If you really want to understand the details of the model, the best place to start is in our published paper that describes the model. Here that you can see that was published in Astrophysical Journal Supplement Series back in 2017. We have the next version of the model called Planet 2.0, which Kostas Sigouridis is leading at the moment. We have some delays with the model, but I want to assure you something that I think there might be some misunderstandings about. The Planet 2.0 version of the model does not have tremendous amounts of additional features compared to Planet 1.0. Most things you can do in Planet 2.0, you can do in Planet 1.0 and vice versa. There are very few additions. We've actually backported a few features from Planet 2.0 into Planet 1.0. So you're not missing anything in using Planet 1.0, which is what we're going to focus on the next 2 days. So some of the things we have used the model for are things like ancient Earth. So going back to 2.9, or in this case, this is a work by my predecessor, Tony Del Genio, in 2018, although we've even done simulations back to 3.8 or 4.2 billion years ago. We've done some ancient Venus things. This is one of our more infamous papers or notorious papers, take your pick, where we have simulated what ancient habitable Venus might have been like. This is from our 2017 paper describing the model, where we have done some Mars, ancient and modern Mars, although without CO2 clouds for the model per se, but we still get some decent agreement with Viking 2 data, as you can see here, at least in terms of surface pressure to go forward in time. This is work that was led by Igor Lienol, one of your tutors. And then hypothetical Venus-like worlds around things like M dwarfs. This is a paper led by Stephen Kane that I was on, looking at Kepler 1649b. There were a lot of problems trying to model this particular system because the planet in question is getting a lot of solar insolation. And in fact, the model didn't like that very much. There are limitations to how warm the atmosphere can be before the model gives up the ghost, as we would say. So we have to be cautious of things like that. Hopefully we'll have time to touch on some of that going forward. Here's another one of our more highly cited papers. This was led by Tony Del Genio for the Proxima Centauri B system, where we did a variety of different types of atmospheres, everything from more or less a modern or an Archean type, Earth Archean atmosphere. The control run in this case was about a 1 bar N2 dominated with trace CO2. And then we went up to things like a 10 bar N2 plus 376 ppm CO2. That's pre-industrial levels of CO2, basically, as you can see here, all the way up to 1 bar of CO2. So those are just a few of the things we've done, also even with some CH4. And then Igor Lienov has even used this to look at our ancient lunar atmosphere, a short-lived lunar atmosphere that's been postulated in various papers in the press. And Igor continues that work with the model, looking at very, very thin atmospheres, which we may touch on a bit more later. And then Chris Kalosis is in a room with us today, has also looked at obliquity studies with the model, looking for hysteresis in the model output, which has been seen by a number of others in the literature, and also spin orbit resonances. And Chris has also even applied geothermal heating that is possible in Planet 1.0, since some of these tidally active systems will have some tidal dissipation and hence some sort of tidal heating also, which can be put into the models at the land surface and even at the bottom of the ocean, if you like. And then we've done very large parameter sweeps. This is a paper that we published back in 2018, where we vary the rotation rate of the model. So each one of the colored lines represents different sidereal rotation periods, everything from Earth at what we did. So the black line of X001, X002 is 2 times Earth sidereal spin rate, and then all the way up to 256. And you can see here that we label the ocean in two different ways. One's called a Q flux equals zero ocean, and one is the dynamic ocean. And those are different ocean types you can run with the model for various scenarios, which we'll touch upon in some detail in some future slides. So I think this slide is really important for many of you who are online. As I say here explicitly, and I'll say it again out loud, really the fastest and most reliable means to get a new planet running is to find a similar one from our previous papers. And in general, this group believes in the ability to reproduce the results from anything we have published. So you don't know what some of these things are that I'm talking about here, run decks, boundary condition files. We'll get into those, what those are, but you can find them for hopefully any simulation in any paper we published online at this URL I put here at the bottom. So if you want to run a simulation that's similar to something we've done before or the same, you should be able to download these configuration files and run the model yourself. In fact, it's a good way to make sure that you're getting results that are reasonable if you're afraid at all that what you're doing may not be quite stuff, is to find a model run in one of our papers, pull down run deck and the boundary condition files, and run the model and see what you get. Always recommend that. Start out with one of our models and then move forward from there. Okay, so now there's some caveats. One of the reasons I say to start with one of the previous models is that there are really a limited number of atmospheres and stellar spectra available. We'll discuss those in detail, time permitting. But it's very important to keep this in mind. You know, if you see a planet, you know, mentioned in the literature that you might like to model, you have to be cautious to see if the model actually will give valid results for that particular planet and the kind of atmosphere you want to model around it. For example, we cannot do 100 bar CO2 atmospheres. Our model is not capable of doing those for reasons we won't have time to go into today. And our model also has difficulty doing microbar or picobar type atmospheres that you might find in some outer moon type atmospheres. As I said, we can't do thermospheric or exospheric type modeling. We don't have non-LTE corrections in this model, for example. So you have to be very cautious when you decide to do a modeling study. We have seen in the literature published papers by people who have taken stock models like the NCAR atmospheric model and published results that got through the refereeing process. Somehow we don't know how, where they didn't change anything. And they modeled an atmosphere around an envelope, for example. Those papers are almost certainly very wrong. Not sure how wrong they are, but they are very wrong. Because you cannot just take a stock Earth GCM and turn the GCM on with a different stellar spectrum. Your heating rates, your rate of transfer, everything's going to be completely out of whack. You have to use the right kind of spectral files for the type of star you're interested in modeling your planet around and the type of atmosphere. This is extremely important. And something that is not mentioned, I think explicitly in the literature, because most people running these models are experts. And that's one of the reasons we run this tutorial, to help you understand what this model is good for, and maybe to help you understand the regimes in which other models are valid as well. Okay, so let's have a list of things that the model cannot be used for. And these are just a few of the things, but one thing we cannot do is we cannot change the mean molecular weight of the model going forward. We have a long-term project to allow this. But what do I mean by that? For example, if you're on Mars today, the atmospheric pressure on Mars changes by almost a factor of 2 throughout the year. That's because of CO2 condensation and water vapor condensation. The model does not allow that unless the atmosphere is consisting of one atmospheric species, because then the mean molecular weight doesn't change. But if you're in a multi-component atmosphere and you have large amounts of condensation of one of the main species, then the mean molecular weight of the atmosphere changes, and then your dynamics in the model are probably not very accurate because they're designed for the mean molecular weight that you start to model out with. I say here super Earths. We have done some super Earths, but there are limitations on how far we can go. The dynamics is a bit fussy about that. And as I say here, where the thin atmospheric approximation is invalid. So as I said earlier on, things like sub-Neptunes, lunar Neptunes. I have a question mark here for super thick oceans. So since we ran the tutorial last, we have made a lot of progress in getting the model to operate on worlds like Enceladus and Europa. And Tony Lepoisontier, who's also with us today. Tony, did you want to raise your hand there and say hi? Hey, I think I forgot to mention Tony was here as well. Tony will discuss that a little bit farther down the line. And then I have here, not above temperatures of 400K and not below 100K, I say except for Titan. That's because our radiative transfer scheme has limitations. So if you think your planet's going to be much warmer than around 400K, the chances are our model's not a good candidate to be running for that system, because the radiative transfer will crash because it's not valid for temperatures above that. It might actually keep running for a while, but eventually will become very unhappy. I also say here we have problems for really cold planets. So, if you take Earth today and you lower its insolation by 50%, and you just run it this way, the planet will ice over, and eventually your ocean will start to freeze to the bottom in the shallowest grid cells. And the ocean doesn't like to be squeezed out of existence, as our dear colleague Max Kelly has told us on multiple occasions when we have complained about this. That's because our model cannot currently change dynamically the surface types. We cannot move from an ocean to a land surface type, which you would do in a case like this, although this is again an ongoing project which we're hoping to improve upon, because we would like to have that capability, because sometimes we want to model really cold planets, or sometimes planets might end up cold for a while and then warm up again, which we see in some simulations. I mentioned here fast spinning planets, so you have to be a little bit cautious about how fast your planet is spinning, because you will undersample the raw speed radius of deformation, and that's very important for atmospheric dynamics. So be careful when you have this idea. We can have a discussion about that offline. But for example, if you try to run the default 4x5 latitude longitude resolution for this model with a 12-hour spin period, you will find out that the model does not sample the raw speed radius of deformation well. And please, if you have questions please ask them in the chat, and hopefully one of the other instructors will try to answer your question. I've already mentioned this about mini Neptunes and gas giants, and I say you remember the 3D acronym, as it says, orbital climate keys of Earth and extraterrestrial environments. One shortcoming of our GCM and other GCMs, we're not alone in this, is that we have what's called the South Pole anomaly, in that the South Pole grid cell always has to be a land grid cell. Although again, we have an ongoing project to try to address this problem. And there are limitations in the atmospheric constituents that are based on what the radiative transfer scheme can allow. So doing pure CH4 atmospheres is not feasible at the moment. We don't have any interest in doing that ourselves, at least not at the moment. But we have a wide range of Earth-like atmospheres, and even up to, as you saw earlier, 10 bars of N2 or 10 bar CO2 atmospheres are also possible. But there are some limitations which we'll get into. Okay. So some things that we want to mention also is that the code repository, which you might have already seen when you downloaded the model, are located at these URLs. And we have a little bit of documentation, although as I said before, generally we recommend that you start with one of the models we've already published and then use that going forward. But there are a few example run decks here. As you can see, the Planet 1.0 Dynamic Ocean run deck. And as you see, the Model E2 Earth run deck. So Model E2 is what ROCKE-3D is based on. I don't think I mentioned that so far, but one of the philosophical choices we made a few years ago was to remain as closely tied to the Earth parent model as we can. And that Earth parent model is called Model E. So we are split off from them a little bit, but in general, we stay very close to them so that we get all of their updates. They're a much bigger group than us, and they do a lot of development. And this is more or less the same model that the people you in the UK Met Office have used. Although it is not the same model that has been used by, for example, Exocam per se, or the LMD group, for example. They split off from their parent Earth models many years ago. So there's some advantages and some disadvantages. The advantages of splitting off is that you're free to do a lot more quick development. But from our point of view, the disadvantage is you don't get the updates from the Earth models, which are typically very large groups of people working on these models for decades. They have tremendous amounts of experience and they're always updating these models. So for example, we've had a lot of updates to the land surface model in the last year, which we probably would not get downstream in the Planet 2.0 if we were not tied to the Earth climate model so closely. Okay, and then the latest snapshots. So, I mean, these are a little bit tricky. Kostas, do you want to mention something about the latest snapshots and what that really means?
Yes. So we have a lot of.
ठीक है मैं ध्यान रखूंगा अभी थोड़ा अभी बात नहीं कर पाऊंगा आ रहा हूँ मैं थोड़ी देर में
I'm sorry.
I think someone should mute.
Yeah.
Please mute if you're online.
So
No, we don't see the bottom of the display.
Okay, I think it's just.
I think that's what you.
What's the matter? Reto, did you say that?
So we don't see the full display. The bottom is sort of cut off.
Oh, the bottom is cut off.
oh, the bottom.
Okay, thank you for pointing that out. Hold on a minute. I will see if I can fix that.
I can see it. I can see it.
Well, other people say they can see it.
Yeah. Well, the bottom line is
Yeah.
latest snapshots and HTTPS.
Yes. Redo, this must be on your side.
Oh, maybe it's, well, anyway, hopefully we can all see that, but go
Okay,
ahead.
So
Kostas, sorry.
anyway, there are official versions of the model that are released and they receive a version number and they stay there in our repository. But then we have individual model versions that for whatever reason one might want them to stay there. Let's say it's a version that you used with for a paper and it's modified from what the standard thing is. So we might occasionally have something like that. There is also a cutting edge version that we have available, which is not really the cutting edge. It is mostly a remnant of past version controlling that we have been doing. But in general, the idea is that you should read from our snapshots. You need to see right next to it, we have a text that explains which version exactly is and which one you are really going to take. And in general, the idea is you should be taking the frozen model versions. So Planet 1.0, model E2.1 probably is the most recent one right now. And if you know that for some reason this one is not good for you, then take another one. But consulting with us is always a good idea.
Yeah, just one notice about snapshots. It may be a little confusing, so I want to explain. The snapshots on snapshot web page, you will always see that each snapshot is basically this current date. So you may think that it was updated like just today or yesterday. That's basically just the result of our script is being set. And that means that it was updated, but it was just taken from the repository this very night and was put for the download. But the actual version will correspond to the version which is in the repository. So if the repository wasn't updated for a few months, for example, for a free frozen model, then basically it will be still the same. But it is advisable, basically, if you start new work, to download the latest version that you see in on Simplex in snapshots page, because it may have like bug fixes or it may some additional features added to even to the frozen version, because we do fix bugs in frozen versions and we sometimes add new diagnostics to frozen versions and sometimes even new features. So basically, better use always the latest one.
Great. Thank you, guys. Excellent.
And by the way, Mike, have been some questions in the chat. I am taking care of them for now.
Okay.
If something comes up that I don't know the answer, I will let you know.
And I can attempt to say that I also don't know. All right, I think just so you know a little bit about the complexity of this model and who's behind what. Here, I have listed everybody who's working on the model, at least in this group, and a little bit on the Earth side of the house, but although very few. Our cloud person, who is, I mean, a real cloud person, Andy does cloud microphysics ab initio studies, and he's in charge of major components of the cloud convection schemes in the Earth GCM, and he worked closely with us. Kostas Ligoridis, who you just heard, and Sunny Harmon are working on atmospheric chemistry for the model, which we'll touch on a bit later. And Kostas is also in charge of the aerosol components. You can ask me about various planets and orbits and things like that if you're curious how to get those working. Our radiative transfer expert is Eric Wolf, who's associated with the University of Colorado. In-house, I've got Andy Laces here, although he has a successor now for the GISS radiation, but generally most users of ROCKE-3D don't use the GISS radiation scheme because it's, while it's extremely fast, it's really only designed for modern Earth atmospheres. If you use anything other than modern Earth atmospheres and installations, you could go very wrong. It's tuned to be extremely fast. That's the main point here. Whereas the Socrates radiation scheme that we use is not as fast, but it's much more flexible. Atmospheric compositions, well, you can ask any of us about that, but I've got Kostas' name down here just to give him more work that he doesn't need. Debugging issues, the three of us, Igor, myself, and Kostas are the main people you should contact first, and we'll farm out any kind of work that we can answer. You'll meet Tom Clooney, one of the instructors, tomorrow. He's really in charge of calendaring issues in the model or rotation rate issues for different worlds, or he's been in charge of taking care of things like odd orbital eccentricities or obliquities, different rotation rates. Nancy King is really in charge of the plant parts of the model, the ENT, as we call ENT. What ENT stands for? What does ENT stand for, Igor? ENT.
It's
Just end. It's from some movie, I guess.
It's Lord
Lord of the Rings?
Lord of the Rings, the ends were the trees.
Okay, there you go. ENT. So Nancy's in charge of that, and though Igor helps her quite a lot.
So it's not all capitals, it's just E capital
E, okay.
and T. Or it's a name.
I'm sure many of you online know much more about this than I do. Igor is also our land surface expert, along with Nancy and the model. And then Tony Lavoisier is really in charge of ocean and sea ice, as you'll see when he gets to his slides. And although we haven't mentioned it yet, we do have our own in-house NetCDF viewer called Panoply. And what is a NetCDF viewer? Well, you'll find out later, but in general, the model produces NetCDF output. And if you want to look at the model results, which you probably have if you followed our directions, you use the Panoply viewer to look at these NetCDF, although there are other viewers, which we'll touch on a bit later. But Panoply is very nice for making publication quality type plots. It's used by people all over the world, and it's a great resource to have here locally. And if there are things, additional features that come up, we can often directly talk to the main developer, Robert Schmunk, about those things. Okay. I think I'll let Kostas take over at this point, describing the different versions of the model, and then maybe we'll take a small break after 5 minutes or so.
So everything here is based on the GISS model E, which is the model that is used for the IPCC reports and for everything that we have been doing here for at least a decade or two. Before that, it was still the GISS model, but it had a different name. But so you will find a lot of different namings of this model in the literature. So it is the ROCKE-3D model is based heavily on GISS model E2, and this is it is in reality a later version of E2, but not the version E2.1 yet. It is some intermediate phase of it. For CIMIP 5, which is the coupled model intercomparison project that has been used for the IPCC report in 2013, the names that we used are GIS E2, and then there is an R or an H, depending on the version of the ocean we used. For CIMIP 6, that was published in 2019, I believe. It was GIS E2.1, and then there were also two versions of the ocean, the G and the A and the H. Essentially, the R became G, but it's the same ocean and evolution of it. And then ROCKE-3D is always using the G or R ocean from the past. So we don't name the ocean explicitly. So for Planet 1.0, as I said, it's GIS model E2 and a little bit later, but it's about that. It's about right. Planet 2.0 that is about to be released is GIS model E2.1, and it contains also what we internally call Tracer C3 branch, which is essentially some changes in the infrastructure that are only affecting for the results by numerical noise, but also some major changes in the tracers code that we will not be discussing in this tutorial, because we will not be discussing about prognostic atmospheric composition here, other than the major gases like water vapor or water vapor things. So these infrastructure changes, including many others, eventually made it to model E3, which will be the base of our Planet 3.0 version, which is yet to be developed. And internally, we have the Planet branch, which is our development branch, but you will not be seeing that in general. Right now, the Planet branch and the Planet 2.0 are the same thing, but that's only for internal use for those of you that have access to our repository. And then for the atmospheric composition, we have three flavors. One is NINT, which stands for non-interactive, meaning that you prescribe the greenhouse gases, and you may or may not have some vertical or latitudinal distribution of those greenhouse gases, and then these stay fixed for the whole simulation. There is a way to create a transient simulation. So, for example, CO2 increasing in a global warming scenario, for example, for present-day Earth, but still everything is prescribed. The only thing that is calculated dynamically is water vapor. And then we also have two versions for aerosols. One is called OMA, which stands for one moment aerosols. It simulates only aerosol mass. And then the matrix, which is the acronym is, I don't remember it exactly. It is calculating aerosol microphysics. So it can calculate aerosol mass, aerosol number, and also aerosol mixing state. We are not going to discuss about those. They have never been used really outside the Earth concept. And we have done an OMA version for Mars that simulates dust. We have done simulations of past Earth, like 500,000 years ago, with dust and sea salt. But we are not going to discuss those in this tutorial. We will stick with the non-interactive NINT version. So we'll stick with that.
Thank you.
Yeah, you want to continue on this?
I think we should.
Okay, so going into the model structure itself now, to go from the higher level science part into the actual way you will be working with the model, there are some important things you need to know what they are and where they are located. First of all, there is, as you've seen in the instructions that we've sent you, there is a file that is called .modelerc that lives in your home directory. And this file contains all the configuration that the model needs to know in order to be able to compile the model. So things like which compiler you are using, where the libraries are, whether you use MPI or not, and you know where to save the output, things like this. Everything is in there, and the model is referring to it at compile time to create the actual configuration to run. Then The actual ROCKE-3D code, which you have downloaded from our computer, from our server, it creates a directory somewhere. You can name it anything you like. For the purpose of this tutorials, we assume you have it on your home directory, and it's called Model E2 Planet 1.0, but it can really be named anything you like. But then inside that directory, there are many things, and 3 of them are very important. One is a template Randex, which is essentially the blueprints that you will be using to create your Randex that will be used to run the model. And we will see what the Randex actually is right now. So for now, just think of it as a file that contains all the instructions of how the model will compile and run. Then the actual Randex are saved in the subdirectory called dex. And these are not the same with the template Randex, no matter how similar or even identical they can be. Their functionality is different, their purpose is different. So you should never use a template Randex to run the model, even when this works. You should always create a Randex from a template in a way we will show you later. And then the source code, which is the core of the model, all the Fortran files, are inside the model directory and subdirectories. You can go next.
Just one thing I wanted to mention, that everything that you do from tutorial and in the future, all your work is done from dex directory. So basically that's becomes your kind of like home directory for work with model E.
Yeah, unless you change the model code when you eventually go to the model directory, but we will not discuss about code changes here.
Yeah.
Okay, so the input and outputs are also important, and these are defined in the model ERC file. The model assumes that you have a shared directory somewhere on your server, that all the input files exist, so all the multiple users that potentially might be using this model will not have to replicate all the input files. There will be a central repository that stores all those input files for general use. And the location is called GCM search path in model ERC, and you can define this directory to be wherever you want it. Then if you want to use a custom file, so in the Randex, when you define all the input files, the model assumes that everything is in that directory. If you want to override that, then you must define an absolute path in the Randex and start with a slash. So you cannot, if you say, I want a file that is called into the GHG directory and it's called whatever, ghg.txt, the file will be called, you will say in the Randex, ghg/ghg.txt. If you want to say, if you have a custom file, then you need to define the full path, like /home/your username, blah, 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 the whole thing. And obviously the files need to be accessible to when you're running the model. So if you are having a computing system that you need to submit a job, for example, and then that goes into a new environment, you need to make sure that the files are available into that new environment. And then the output files are saved in again, the main directory is defined in .model ERC, and they are under the save disk variable. And you can, it needs to be a place where it has a lot of disk space, really a lot. The model output is very verbose. It's depending on your configuration. If you're using the fine resolution, for example, it can be very, very voluminous. So you need to be aware of that. And for your convenience, in the dex directory, this output directory is also being linked by a soft link. So some people go to this save disk directory and work directly from there. Others, like myself, use the soft link from the dex directory. It makes no difference. The important thing is that you need to have a lot of space to save the output. Next.
We're talking in tens to hundreds of gigabytes.
Yeah, I mean, if you use the file resolution with multiple traces that I am using, you go into the terabyte regime, yeah. But in general, hundreds of gigabytes is probably a correct ballpark.
Yeah, be very cautious about your disk usage because the model will crash if it doesn't know where to write the data. It might take you a little time to figure out that's why it cracked. Yeah, so make sure you have a lot of available space.
And in general, there are several ways to recover a crashed run. We will discuss about that. Yeah, it's running out of this space is very common.
Yeah, but don't be afraid. I mean, to run this example run decks which we provide on your laptop. It's also don't produce that much output.
Yeah,
Probably still a lot, but not.
well, if you run it for a month to see what happens, it should be manageable.
Yeah, but to get a feel for it, run those. You'll see how large the outputted ACC files, as we call them, the netcdf files are, and you can get an idea for each month how big they are for your particular setup, and then you'll know. Like if I run for 10 years, it'll generate X amount of data.
And there are also ways to manipulate what actually the model is saving, and that increases or decreases the model output. And we will get to that as well.
But on your laptop, you will be limited by time, not by the amount of space. Typically.
And
We'll get to that.
And Mike, I see that there are questions that I am not able to answer while I'm speaking.
Okay.
But can you go next?
Well, I thought we would take a break.
Okay,
It's about
perfect.
time for a break. So we will pause the recording.
To the full hour?
Change, or I will try to pause.
No, you cannot pause. You need to.
I need to stop it. Let me just stop the share for a moment and then see. Okay, everybody, we're back now. And Kostas will continue. We'll probably finish this section a little early, and then that'll leave us some time for questions before we take lunch. So let me share the screen again. And I'll let Kostas take it away.
Okay, thanks. So I am, yeah. It's funny,
There,
why?
that's where we ended last time.
Can you take your mouse from there because I see a white line on my screen?
Yeah, I'm trying to.
Okay,
Is that better?
perfect. Thank you. So if you followed our instructions for installing the model, then you will. No, we are in the next slide. Yeah, then you will already have a run deck created. You can take a look at it if you want while I will be speaking, but otherwise, the abstract part of the run deck is right in front of your screen right now. So the run deck contains a lot of different components, all of which have a different purpose. So let's go to them one at a time. First of all, we have the object modules, which are essentially the files that the run deck is that you are asking to compile. It contains the file names listed in the model directory, excluding the extension. So if it is a .f or a .f90 file, it doesn't matter. Probably there is a priority if there are both files exist, but I don't know about that. I mean,
There is a priority, but
Yeah.
I've forgotten what it is.
Yeah.
I think it's probably F90 now has higher priority than
Okay.
F.
but
And
they,
then C, you also can, no, C,
no, I don't
you
think
can,
so.
you can use C in the latest version, but not in client one.
Okay.
I don't think I put it.
But let me just
So-
reemphasize something very quickly about the run deck. This file contains everything that the model needs to run. That's what we're going through now. So if you look at the template run decks we gave you beforehand, you could look at one of those while Kostas talks about this stuff, and you'll see these things in there. That's what I would recommend. If you have a text window open, you can look at it. So go ahead.
Yeah.
Kostas,
Yeah, and
sorry.
I'm just tempted to explain people why we call run deck, because many people actually don't know what it is. It is called that way because the model originally was run as a deck of punched cards. So a run deck, it was a deck of cards which was added at the top of the deck of the main code, and which was basically explaining how to run the model. So the name remains. Run deck is actually a deck of cards which.
We're talking about the 1970s.
Yeah. Yeah.
It tells you how old this model
That's so
is.
crazy.
A true legacy model.
Yeah.
Punch card.
Wow, I wasn't even born. So, okay, so in essence, you list all the files you want the model to use to compile, and then there is a block that is called components, and in those components, essentially these are standalone versions of the code that live in subdirectories into the model directory. So there is one that is called end, there is one that is called shared, and there are several other components. We don't need to go into details about that. The important thing is that these components, meaning subdirectories in the directory tree, they have their own make file that describes what the model should do to compile them. And you don't have to list the files in the components. The make file in the components is responsible for that. And then depending on the component, you can provide some options on how to compile it. And these are listed in the component options. So the components might have different ways to compile. For example, in the case of the vegetation, you have one or more plant functional types that you can use, and you define that in the component options. These are things you will nearly certainly never touch. But in case you do, you need to remember that if you change the components or the component options, you will probably need to make a clean before compiling again. You don't need to do that if you change the object modules, meaning the files that need to be compiled. Even if you edit those files, if you edit any Fortran file, the model will figure it out, and compiling again will do what it needs to do. But if you change components or its options, you have to do a make clean beforehand. Then the other big block of the run deck is the block that is called data input files. And this is exactly that. It is a list of files that the model will need to run, and it needs to read them as inputs. And in Fortran, you need to define into the file name, into the source code, which file name the code will read. And that is inflexible. So if you change input files, you will have to change the code. So that is not the way we have it. So what the data input files does is that it creates soft links of the whatever named input files you have into some standard input names. So if you are looking at the run deck and you can see at the very beginning of the data input files, maybe even first, there is a line that says AIC equals something. So this means that the code will try to read a file name named AIC, and then the compilation process will create a soft link from the file that is listed to equal that into a file called AIC, and then the model will read that one. So it is a very flexible way to modify input files without having to modify input file names, without having to modify the model code itself. So there are several files there. AIC, for the record, means atmospheric initial conditions. There is also a GIC, which is the ground initial conditions. There is an OIC for the ocean initial conditions. There is a topography file. There are rivers. There are a lot of things there. So we can go to those files as needed. It will be a waste of time to just go through the whole list right now. First of all, because it will take us forever, and second, because you will probably forget about all those things down the road. So I will move to the next part of the run deck, which is called label and name list. This essentially defines the run name, and also it contains a comment. The run name, we frequently call it run ID. And then it is essentially the file name of the run deck without the .r, which is the extension of the run deck. And then this line under the label and name list contains a comment that will be included in all of your outputs. So if you are someone not like me, you should be updating this line to reflect exactly what the simulation is doing, and then you will have it in the output. I frequently neglect to do that. Frequently means always, and but it's not the recommended action to take.
He's not alone. I think
Yeah.
almost all of us.
Nearly everybody ignores this line, but at times I hoped that I had done the right thing, because I was wondering what a simulation was, an old one.
Yeah, I guess we want to mention that typically copying one run deck to another run deck and just modifying something works. But if you don't update the source labels, then sometimes you will see some confusing information in printouts, and mostly not terrible, but yes, it's nice to update those. But if you create a new run deck the right way, I guess somebody will explain later, like with the right command, which will take template from templates directory and create a run deck for you, then everything will be done automatically. So you don't have to modify anything in that run deck all these days. Names will be updated.
Yeah. And then we go to the to a very important component of the run deck, which is called, it starts with twice ampersand parameters and ends at nearly the end of the run deck, which is by the end parameters line. And this contains information that we are passing into the model that explains how the model runs. So the idea is that for certain parameters, you want to modify them during the compilation or during the model run, and you don't want to go inside the model code and modify things. So if you are doing, for example, a large parameter ensemble and you want to explore the range of values of any parameter inside the model code, literally any, what you need to do is you go inside the model code and you add a line or two that says essentially to the model, you can take the value of this parameter from the run deck. And then you create 20 different run decks with 20 different values into that parameter, and you run them separately, and you don't have to create 20 copies of the model code. You only have 20 run decks, and then the model code gets the values from the run deck. And this is an extremely powerful way to create, to explore parameter space or to modify things that are frequently needing modifications. For example, if you want to simulate several planets, you have different rotation periods, different eccentricities, you name it. I mean, we use that really a lot, and it's extremely important.
You don't have to recompile
And
every time.
exactly, you don't even need to recompile if you want to change things. And even better, for more advanced things, you can even stop the model, modify one parameter of those, and then continually will continue with the updated parameter. So obviously there are limitations of which things you can change. You cannot change the rotation period as the model goes on. But there are other parameters that you might want to change, especially when it comes into debugging or high frequency output. So this list is very long, depending on the run deck. It's there are many things that we can discuss about those. Do we discuss about master year and stuff later?
I don't remember. Maybe we will.
I think we will, yeah.
I think it's
So I'm not going to say something specific about those parameters right now, but we will get back to those earlier. So one of the key things that we define in those parameters here are values that are related with the model tuning, variables that are related with how frequently we call radiation, how frequently we save the output, what type of output we save, what's the model time step, including many, many others. And then a key thing that appears at the very end of the run deck is 3 lines that start with input Z. And essentially you are saying there the start and end times of your simulation. So you say the year, the month, the date, and the hour that the model will start, and also the year, the month, the date, and the hour that the model will stop. We will be discussing about the calendar tomorrow. So let's keep it simple right now. Think of Earth only. Don't try to think of any other weird planets. So if you want to do a 1-year simulation, you start your simulation, you define the year I and the initial year, and I think I have it in the next slide. Can you go to the next slide? No, it's further down. Okay, so I will discuss the details about the input Z later, because it exists in a different slide. So let's go to the key template.
Just one thing I wanted to mention about the ROCKE. It is parsed by our in-house code, so please don't assume that you have like freedom to do something that you don't see in this parameter in this file. For example, parameters are parsed by our in-house code, so they look very similar to name list in Fortran, but it's not. So if you don't see certain syntax in our examples, please don't try like to use some shortcuts that Fortran is doing. They are not supported, and preferably try to avoid trailing spaces. Care was taken to treat them correctly, but still sometimes they may cause problems. Basically, try to keep syntax as close to what you see in examples, and then you will be fine.
Yeah, I can second that. Be careful about trailing spaces. It has burned many of us many times in the beginning.
Especially the .model ERC file, trailing spaces in non-comment lines is forbidden. It will not work.
Well, we try to fix most of those places, but still, yes, assume that you shouldn't have any trailing spaces because you may cause a problem.
I mean, if you have trouble getting the model compiled or run, the solution first is always to go back to the original template that you created from the templates directory in the ROCKE directory. Make sure that works, and then make your changes before you write us and ask us what's wrong. Please.
And one thing to mention for the Randex is that if you want to put comments in there, feel free. The comments are start with an exclamation mark.
Yes.
And they can be either full lines or partial lines, whatever.
Yeah, and I think there was one, actually, can we go back?
Yeah, sure.
I think the most important part what is missing from this slide, it's the part which goes before the object modules. It's a part which defines all global definitions, so like basically CPP preprocessing options. We will probably be discussing those later, but those options, they are specified actually at the beginning of the ROCKE. So if you look at any templates, you will see this section with global.
Can you go back and forth, because I edited the file?
Oh,
yeah.
No, it doesn't. Maybe you need to restart it. It doesn't matter.
Well, yeah.
It's
So there is an option. I mean, it's self-explanatory. So you just specify all global CPP preprocessing options there, and they will be visible in the files. And how they are visible, I think there will be a slide later which will describe basically how they.
And you have them. If you look at one of the template runducks you should have built from, you'll see these preprocessor directories in the very top.
Yeah, and they are very important because they basically decide how you compile the code for different options, what to include, what not to include. So they present nearly in every ROCKE because they need it.
And often we put the bug fixes up there too, explicitly. So you'll find.
And
I think we will be discussing about that later.
and even before that, before those preprocessor options, there is a section where you can describe what the model is. It's not used by the machine, but it's for you, that you remember it on why you set up, why you ran that experiment, and any notes that.
Yeah, that can be very useful. Say a lot of us use it, but it is
For your future self. So
Yeah.
it's
For my
pretty
future.
small.
Yeah, as I
Why
mentioned,
run this?
yeah, as I mentioned, this file is parsed by our in-house code. And there is a rule that everything that is written in this file before you specify your preprocessing options is a command. So it will be just ignored, but it's a space for you to describe your run, except the first line. The first line should start from the name of your run, because at least like first characters of this line, I think I used for record keeping, so it will appear in your printouts. And
So starting,
Is this the first line or the lines with the name list? With the
both, it's kind of confusing, but both of them, I guess, are used.
so the name label and name list and the first line are
Yes.
both used.
Yes.
Okay.
So starting from the second line, you can add comments there.
yeah,
too.
Before the
Whatever you want.
preprocessor directives, you don't even
Yeah.
need the exclamation point.
Okay,
Just right.
Yeah, just any text other than like keywords.
Other than preprocessor options, you can say anything you
Yeah.
want.
okay, good, because I wanted to add notes, but I wasn't sure how
Good.
flexible.
Well done.
Yeah.
Yeah. Thank you, Rado.
Okay, so let's move on. So the key template run decks for Planet 1.0, they are those four essentially. And the naming of the run decks can be anything you want. We have a character limit. I think you cannot name a template or a run deck. You cannot use more than 32 characters. I have seen issues at times with more than 30, between 30 and 32. So I would say keep it to 30. But anyway, everybody invents their own cryptic way to define their simulations. So for Planet 1.0, we have P4SM40, which is the prescribed sea surface temperatures. P is for planet, 4 is some heritage from the past, you just don't ask. It's gone in Planet 2.0. And then S means Socrates, M means medium resolution, which means 4x5 degrees, and 40 means 40 layers. Then we have P4SQM40, and Q means it is the Q flux heat surface fluxes in the ocean. And
We'll get into details about what this means later.
yeah, we'll discuss about that. And then we have P1SOM40. Forget about the difference between 4 and 1 here, just pretend it doesn't exist. O means dynamic ocean. And then, so in essence, those three run decks, other than the ocean itself, they are exactly the same. And then we have PS Mars, which is a desert planet. It's not exactly Mars, but it is our first attempt to do Mars. So we do that way better in Planet 2.0. But if you want to start a simulation for a planet with no ocean, this is where you are starting from. And yeah, Mike already mentioned it. For configurations, you will be tempted to simulate something that the model allows you because there is a configuration option there. Don't do that unless you are certain that the model can actually do it, because even if the model doesn't crash, you need to be careful about it. If you go to a warm planet, which is still below our 400 Kelvin threshold, and you end up with like 50% relative humidity, 50% water vapor in the atmosphere, it's not right. The model cannot handle it, even if it will not crash. So please ask us if you try to go to extreme cases or do something that you have not seen us doing even remotely.
I want to second that very much. We're very happy to vet the experiments you want to run, because it would reflect badly upon you and upon us if you publish something that was complete rubbish.
Yeah.
So we prefer that if you're doing something that's a bit outside the box, just write us. We'll be happy to tell you whether that's viable or not, or which spectral files, which we'll talk about later, you should use for data transfer, or which ocean parameterizations you may want to consider using, etc. We strongly encourage you to reach out to us in this respect.
And everybody is busy here, but we will be answering those questions to you.
Absolutely.
So for Planet 2.0, we have many more run deck options. We have, so over here, you see in those top 3 run decks that we are changing the ocean only. In Planet 2.0, we changed the radiative scheme. It is not only Socrates. We changed the resolution. It is not only medium resolution, it's also fine. And we also changed the composition of the atmosphere even. So there will be many more. And as Igor already mentioned earlier, do not confuse the template with a working run deck. These are different things, even if they look nearly the same or exactly the same.
Yeah, the template directory has a lot of files in it, and when you build a run deck, it's pulling several files from the templates directory to build your run deck. So you can't just take a stock run deck name sitting in the templates directory, copy it over to your decks directory and run it. It won't work because there are a lot of files missing from that. So the code combines files in the templates directory to create a proper run deck in a not transparent way. So,
Okay, let's go next. So, yeah, if you want to take a look at run decks, I mean, we don't have to do that right now. You can compare the ones that we're showing you here. So we can discuss P1, SO, and 40 if you want. You can compare the differences between the QFlux run deck with the dynamic ocean run deck. You can compare the dynamic ocean run deck and how it differs from the Mars run deck, and there will be many differences, including source files that are irrelevant, input files that are irrelevant, etc. And in general, we have this documentation page that you can see in this link that lists all the variables from the model. It is an automatically generated page that is that contains also some documentation if present in the model code, and it's an easy way to access everything with that. If you know how to use grep, you might not need to go to that page, but that page will be a clean way to find out the variables, because sometimes grep will be very verbose if you're looking for something like, I don't know, temperature, that the variable is called T in parts of the code. So it's not helpful to grep T, for example.
And always use the -i option to make it a case.
Yes.
Insensitive. Because
Yes. Don't assume that everything follows the same case sensitivity throughout the model code, or even in the same subroutine. It's not, Fortran does not know what case is in variable names. So we are not consistent with it because it doesn't matter. It's not necessarily a good choice, but it is. It is a choice.
and as Chris wrote in the chat window, we'll go through some of this tomorrow in detail.
Yes.
These run decks.
Okay. So the input Z part, which essentially tells the model for how long to run, is really important. So there are 3 lines that I mentioned earlier. The first line is the year I, which tells the model when to start. Then it's the line year E that tells the model when to stop. And essentially, you need to remember that this is, if you think of every model time step as the beginning of a time step and the end of the time step, the year I tells the date, the exact time, including hour, of the beginning of the first time step. And the year E says the time and hour, the date of the end of the last time step. So in this example, the year E of 1910, month 1, date 1, means that it will not simulate January of 2010 of 1910. Because this is the moment it hits January, it will immediately stop. And then there is a third line that starts with I start 2, and in which essentially you say to the model for how long to start what we call the setup hour. So about this setup hour, the model, when it starts at the very beginning, it does what we call the cold restart. it is not necessary, and cold meaning it starts from initial conditions. Restart should have been start, to be honest, cold start instead of cold restart, but it's essentially the model always wants to restart rather than actually start. So what we do is that from whatever conditions we have at the very, very beginning of the model simulation, we run what we call this setup hour, and the model saves a restart file, and then from that point onwards, it continues, it keeps restarting rather than starting from whatever conditions we told it. So whatever exceptional things need to happen will only happen during this setup hour. So we call it setup because it is setting up things for the restart files to be saved. And we call it hour because it is typically only 1 hour since the beginning. So if you see the I*2 line dates and compare them with the year I line dates, you will see that the difference is only 1 hour ahead. It can be longer, it cannot be shorter. It can be longer if you are planning to, if you are doing debugging, and this is what I typically do, is that I do the setup hour to be a day long, and then I run all my simulation in 1 day, and I don't have to stop the model, save the restart file, and continue. You can easily do that, but typically it's a 1 hour thing. The other two things I want to mention in this line, the I*start line, is the actual I*start. This is a cryptic way of how the model actually starts or restarts. I*2 means it starts from initial conditions. So you define some initial conditions file for the atmosphere, the AIC I mentioned, the ground, the GIC, and the ocean, if present, the OIC, and then the model starts from those conditions. If you start with I*9, then you essentially provide only an old restart file, and the model starts from that. And then there is also I*8 that is a kind of a different flavor of the same thing. It is used differently. I don't think we need to cover that right now, but it's in essence, the I*start tells the model, if it is 2, start with initial conditions. If it is other than 2, like 8 or 9, start from an old RSF file. And then internally, the model has other I*start values that we will not use in the run deck, there are numbers like 10, 11, 12, etc. And then I*rand-I is something that is related with how radiation handles clouds, and it's it affects a random number generation for the cloud overlapping scheme. We don't have to go to many details about that. Another important variable for the run deck, though, is in one of the parameters that I mentioned, is a line that says master year equals 1850. So remember that this model comes from an Earth parent. So a typical configuration for this Earth model is to run a pre-industrial atmosphere, and the pre-industrial year is the year 1850. So when this happens in the Earth model, it says essentially the simulation goes into the input files and selects the year 1850, including all the inputs it needs, like prescribed ozone concentrations and the aerosols and the greenhouse gases, and sets them all to 1850, and then runs the year 1850 continuously. That's what they do for a pre-industrial control simulation for any Earth runs. Since for our case in the planetary simulations, we don't have actual transient simulations in any planet other probably than Mars, even if that. In essence, all those input files remain constant for the whole simulation. So in practice, what we do is that we always run a control simulation. So you need to, the year means nothing, right? If you are simulating a Proxima Centauri planet, you don't know anything about years or anything. This is just an index. So we just kept this 1850 just for historical reasons, and then we assume that when there is something that is calling out for a particular year, we call it 1850. So if you go to the greenhouse gases input file, then you'll see that we set the concentrations of the greenhouse gases present on that planet to be representative for that planet's year 1850. It's only an index, and it doesn't really mean anything. And then the years used in the input Z lines, 1897 to 1910, are again only index numbers. So when you run your simulation, you will see output files being created like January 1897, February 1897, etc., until 1910. These are again only index years. So you know that the year 1897 is your year one. What we frequently do is that we start year I from 0001 and we move on. So it is truly an index, but it really doesn't matter. It's just an index. The only time it matters is if you set master year equals 0. When you do that, then you essentially tell the model to run in transient mode. And for Earth, this is how we do the historical simulations, for example, from 1850 into present day. We say master year equals 0, and then every year the model updates the greenhouse gases, for example, to reflect the actual year. Then, if you have the year I and year E exactly as you see them in your screen right now, it means that the model will run exactly those years. So in the output, when you see 1910, it is not an index. It is the actual year 1910. And again, this doesn't matter in our purposes. So I don't think that anybody of you will be using master year equals 0. I think that's all I had to say in this one.
Yeah, I think this, the end of this slide or the next slide are.
Yeah, I think I want again mention like for this inputs part of the run deck that order of basically variables is important. Well, it's not that important. This inputs block is written as in syntax of name list, Fortran name list, but you see that year E, for example, is repeated on the second and on the third line with I star. So basically, the rule here is that reading is from top to the bottom, and you can override parameters which were defined before current line. But the line which starts with I start equal to something, so basically here it is overwriting year E, month E from previous line. But it overwrites it only when I start equal to 2 is taken into account. So actually, how it's done in when your model starts, if you start the model as cold restart, then your I start equal to line is present. For any other restart, this line is removed on the fly. So actually what Fortran is reading the same block, but without I start equal to. So it's important to basically put this I start equal to 2 line in the right place, basically at the end of this block, and list everything that needs to be listed for cold restart only on this line, because this line will be removed otherwise for non-cold restarts, for normal restarts when you just continue the model.
So again, don't move things around in the run.
Yeah, basically just use the phantom armada that's written here and you will be fine.
Okay, in previous years of the tutorial, we actually had you do some interactive stuff. So I'm just going to skip the next slide because you should have done some of this before the tutorial started. So we're going to continue on with tracers, which Kostas is our expert about.
Right. So this is mostly advertisement because we will not be discussing about this here. But thus far, we discussed about prescribed atmospheric composition. You know, I was saying here 1815, the model reads in stuff like ozone, but we can turn on chemistry. We have the CDM4 mechanism, in case any of you know it, it was developed for urban pollution and then expanded to simulate cleaner atmospheres. So we can do stuff as long as oxygen, molecular oxygen is present. And we also have 3 flavors of aerosols. which might be important for whatever planet you are simulating, if there are any aerosols there, including hazes and stuff. So OMA, as I said, one moment aerosols, it assumes a certain size per aerosol component, and that size stays fixed. So it essentially simulates only the aerosol mass. And then we have matrix that simulates size distributions, and it's a model, which means it takes several modes that it assumes they are log normally, the aerosols in every mode is log normally distributed, and then you combine log normals to calculate the full aerosol size distribution. And then we also have Thomas, which has been abandoned into our future model versions because we just don't have the human resources to maintain it. It's more expensive than matrix. It is sectional, so the whole size distribution is distributed into sections, and then mass moves from one section to the other. And then you can create more complex size distributions because there is no log normal requirement. It freely evolves, but it's more expensive because it needs more tracers. So these are the things we have, just in case anybody wants to use ROCKE-3D or its parent version, which is also freely available, Model E, for say Earth applications, then these are your options, and feel free to reach out to me if you are interested in that. And by the way, in case we haven't said it already, this tutorial applies exactly for the Earth version of the Model E. If you know how to run ROCKE-3D, you know how to run Model E. So
I don't know if you really want to go into much of this. I will also just.
yeah, I can say one thing in the previous slide.
Okay.
So this is about the prescribing composition. Some things are uniformly distributed. Let's say oxygen on present day Earth, at least in the lower part of the atmosphere that we're simulating, CO2, but other things are not. Methane is not uniformly distributed, ozone is not, and then other short-lived things like dust, sea salt, other aerosols are not, and obviously clouds. So we have in the prescribed model configuration, we have the option to say, here is a methane concentration, keep it fixed throughout, or here is a methane concentration and some imposed distribution of that.
Seasonal distribution.
Even seasonal. Okay, I was not aware of that we do it for methane.
I thought for O3 we do it.
Oh, for all three, yes, of course, because it comes from an input file.
Right.
But methane, there are some lines in the code that actually kind of skew the distribution, the single value that we provide for methane, it skews it to create some spatial distribution. So we can play with those things. Things are not, it is easy to go for uniform greenhouse gases. You might need to do a few lines of coding to go for something that varies with that, but we can do that. Okay, I don't want to spend more time on that. So before finishing, I think this is the last slide, right?
And then we just
For the lunch, before lunch.
or we can also have 20 bits of the ocean stuff. It depends.
So there are some random, some things that I would like to mention that are related with the simulations, and you need to know those. So first of all, there is a file that is called I. It is an uppercase I, and it is saved in where everything else is saved during model setup, and it is used by the model. In practice, the I file is a complete copy of the run deck when it comes to input files. So everything that you change related with input files goes in there, and this is what the model reads while it's
You need parameters, not input files.
The I file contains input files.
Parameters, so, but also input files now, but not sure it point one then.
Oh,
most important part
okay,
is,
the input files are saved
Yes.
to,
No,
Yeah.
it's all.
in
It's
addition,
It's
yeah.
both.
Both. It's
Yeah,
both.
both.
Yeah, but mostly it's parameters. I mean, input files just used for some weird stuff that you can basically ignore it.
Okay, so it contains both input files and parameters.
Yeah.
So the model is reading that. So if for whatever reason you want to modify something as the model is running, so you stop the model, you should not modify the run deck. You should modify the I file. And also the I file contains some unexpected information. The date of this file, the actual timestamp on the file system matters. So if your model crashes and then you want to restart it, there are some rules in the model that I don't understand completely, but they don't matter either way. The important thing is that the model will try to check the date of the I file, and if it is older than the date of the crash, it will tell you, hey, you haven't done anything, so I'm going to crash again. I'm not running. So you have to do something about it.
It'll also tell you.
Yeah.
Okay,
so,
that was put in because we for long runs we start them automatically, and we don't want to restart every hour the same run that crashed after it crashed. So that's why it's manually we wouldn't need it, but for automatic resubmission we do need this was put in for automatic resubmission.
So in
Yeah.
practice, in a real world example, in your case, if you don't have an automatic restarting, if, for example, the model crashes because you ran out of disk space, there was nothing wrong with the model itself. You just ran out of disk space. So you empty up some space, the model will refuse to start unless you run this Linux command that is called touch, that actually modifies the timestamp of the file to present to now. So
by the way, the safest way to do that is actually to erase the file run_status. That will always work. Then it will start.
Without touching I.
With touching I, usually works in 99% of the case. The other one works
I've
in
never had it
all
done.
cases.
Yeah, so there are multiple ways you can do that. So either you remove the run status or you touch the I file, and then the model is happy to continue again.
The model will tell you touch.
Yeah, the model will tell you that. If you try to run a model and you have not touched I or deleted run status, the model will tell you touch the I file to continue.
But the main reason actually that functionality wasn't reused, I mean, I guess not even for crashes, but pretty much you just don't want to restart the model if the run has already been finished. So that's what model is trying to check. So if you if you have run the model and basically it went all the way to the ending year, then you don't want to resubmit this model to your basically whichever like system you use to start jobs on your computer, because it's kind of wasteful. So basically it just looks for ending dates, and it looks what was the date of I file, and it assumes that if I file was not modified, so it has old timestamp, then that means that the run has finished and you didn't decide to basically to continue by changing the end date. So that's why the model would not start, but yes, it will tell you that basically you have to modify I file or touch it.
We're running out of time.
Then there is again, for probably a flag for automatic restarts is a file that is called log. It contains nothing, but it exists. It's just an empty file, and it is present while the model is running, and it's being deleted when the model stops gracefully. So if your model crashes, then this log file will remain there, and in order to continue the simulation, you will have to remove it. Then if you are modifying the model in any way, either the code or the input files and stuff, and it crashes for reasons you don't understand, compiling with traps is also a good idea. And the way you compile with traps is it's right there on the third bullet point. And essentially, you compile the model and you append this command as you see it in the command line. I think the -00 is not necessary anymore. I've never used it anyhow.
Well, sometimes it
Yeah.
helps. It's just extreme case. I mean,
Yeah.
if nothing works, then
Yeah.
this is
So
the best
I
version.
usually only use the first part of it, compile with traps equals yes, but yeah, the extra flags are also useful. And you need to remember that every object in the model needs to be compiled with that flag. Otherwise, for that object, it will not be enabled. So you need to make clean to compile with traps to have them available for the whole model code. But traps slow down the model because they introduce a lot of runtime checks. So you don't want to run with traps during production. So when you are done with debugging and you found the problem and you fixed it, you must again make clean to make the model faster and compile without traps. And then lastly, if you have a model simulation that is running and you want to pause it, you run the command that you see in the last bullet. SSWE, and I'm certain Igor has a story to say about this, and how it created, but you run the SSW. Let me finish and you'll say the story. And so you run SSWE and then the run ID, and essentially you tell the model the next time, you don't tell the model to stop immediately, but you tell it the next time you can stop, do so. So the moment you run it, the model will not necessarily stop right away. It might, depending on how fast your computer is, in which part of the simulation is, the configuration, you will run, it will just need to go to the place where it can save its state and stop. So it might take like a few seconds, half a minute, something like that. And then the model stops, and then you can continue it whenever you want. And
yeah, well, I just want to add that actually the model has also functionality to work gracefully with signals. So basically that means that should work. I don't think we check it often, but basically if you are running on your laptop, if you type Control-C, it will be the same as executing this command, which means that the model will not stop immediately, but it will try to continue until it can write checkout file and say basically stop gracefully. And the same thing should be happening if you submit your job properly into batch queue on your supercomputer. That supercomputer should, when you run out of time, it should send a signal before, like if maybe a few minutes before you're running out of time, it should send signal 15, and that will also be trapped, and it will have the same effect that the model will try to stop gracefully. It doesn't always happen on all systems because you have to kind of tune such things. So you may talk to your sysadmins about it, but in general, that's how it should work.
Okay, we're running a little bit late, so we'll take a pause now, and we'll come back at the top of the next hour. So
1 o'clock Eastern.
1 o'clock US Eastern time. And we'll stop. So